Now let's continue with our lecture on differentiation. Now we are doing second differentiation. What does this mean? It means differentiation of the initial differentiation. Differentiation of the first initial differential value. How do we obtain it? Let's say we have a function y equals fx. And if I have function y equals fx, I can differentiate and say dy dx. It will be f. You can see with the notation here, x. Now if I want to get, and you know how we got this one? It was d dx of y. That's how we got this f complement x. You can see. So if we want to get the 2y dx squared, we are going to get it by saying d dx dy dx. You can see this one became 2, this one became squared. That is just a form of notification, form of representing it. So this one can now be f double complement x. That is all about it. So for you to get this, it is a must that you get this, at least at this level. It's a must you get this one, then you get this. Now let's look at some examples, just few examples to illustrate and understand this, because there will be lots of reason to apply this to make our work easy. Now before we go into solving some questions, I want you to have idea of what this second differentiation is like. Now if we have a curve like this, okay, let me just make it like this. And I draw a graph for its differential value. The differentiation, the first differentiation. If I should draw a graph for it, let's say the graph looks like this. You know, that is, I make a table for this one of the graph. The graph, let's say it looks like this. So, this one too, if I should make table for this one and I draw graph, I might have straight line, I might have straight line, and I might have curve at the same time. So that is what it is like. So just view the y dx as a new function. Again, a new function separately, like the initial function y has gone. That is how you will enjoy this topic very well. Like that one is gone. You are now doing the y dx for this one. Oh, the y dx, please. So you are now doing the y dx for the y dx you got initially. That's all about it. But let's do this one. You will see the various ways where it is applied. By the time you go to the stationary points, you will enjoy it better. Now let's start with the first one. The first question says 4 equals xy. And since we have it like this, we can easily make y the subject of the formula. So we don't need to view it like implicit function. So we can now say y equals to 4 over x, which is 4 times x minus raised to the power minus 1. So we can now say dy dx will be equal to 4 times minus 1 into x raised to the power minus 1 minus 1, which is minus 4 x raised to the power minus 2. Or you can say minus 4 over x squared. Simple. Now let's quickly do the 2y dx squared. The 2y dx squared will be equal to minus 4 into x, okay, into x times minus 2 times x raised to the power minus 2 minus 1, which is 8 into x raised to the power minus 3, which is 8 over x cubed. So this 8 is positive here, this one is negative. So that one is handled. Very simple, you can see. Now let's quickly do another one. Here. Oh. Y equals x cubed plus 3x squared. Oh, sorry. Y equals to x plus 3x squared minus x cubed. Sorry about that. Okay, the next one. Y equals to x plus 3x squared minus x cubed. So let's quickly do it. dy dx will be equal to 1 plus 2 times 3 times x raised to the power 2 minus 1 minus 3 times x raised to the power 3 minus 1. So this is 1 plus 6x minus 3x squared. Very straightforward. Now, we have known how to do this one easily now. So, the 2y, the x squared, is equal to 6 minus 3 times 2x, which is 6 minus 6x, which is 6 into 1 minus x. That's all. Very simple and straightforward. Now the next one says x equals theta minus sine theta. Y equals 1 minus cos theta. So let's do the x d theta. You can see this one is a parametric equation. The x d theta is equal to 1 minus cos theta. The y d theta is equal to minus sine theta. Sine theta. You remember the differentiation of cos is minus sine theta. Now, what is dy dx? You can now do that one by saying dy dx is equal to dy d theta times d theta dx. And that is sine theta times 1 over 1 minus cos theta, which is sine theta over 1 minus cos theta. And for me, I observe something. If I multiply this one by 1 plus cos theta, and this one by 1 plus cos theta, it gives me sine theta plus sine theta cos theta over 1 minus cos squared theta. So what does that give me? It gives me sine theta plus sine theta cos theta over sine square theta. So 1 sine theta. So this one is giving me 1 plus cos theta over sine theta. I can even say cosec theta plus tan theta. So you can see it's very interesting. So which means that for my the x now, I can work with any of this. With any of this. From here down here, I can work with any of them. Now, for us to get the 2y dx squared, we have to differentiate this. So let's go ahead and do that. The 2y dx squared will be equal to d dx sine theta over 1 minus cos theta. And you can see this one is in theta. It's not in terms of x. So we have to look at another way of doing it, which will involve chain rule. And that's going to be d theta sine theta over 1 minus cos theta. D theta dx. That's it. Now, so let's quickly do this one. And that's going to give us 1 minus cos theta. I'm using quotient rule into cos theta minus sine theta to minus sine theta. You understand? The differentiation of this is minus sine theta and this minus there. Divided by 1 minus cos theta all squared. And what is the theta dx? That is 1 over 1 minus cos theta times 1 over 1 minus cos theta. So you can see, very simple. Now I have cos theta minus cos square theta minus sine theta. sine square theta minus sine square theta over 1 minus cos cube cos theta cube all cube. This one multiplied by this. So I'm going to have cos theta minus sine square theta plus minus cos square theta plus sine square theta over 1 minus cos theta cube. And you know that from our trigonometric identity, this is 1. So I'm going to have cos theta minus 1 over 1 minus cos theta all cube. Do you notice something about this? If you take one of this and this one, and you cut it, it's going to give you minus 1 at this place. So let's continue. Then, so the 2y, the x squared, will be equal to cos theta minus 1 over 1 minus cos theta into 1 minus cos theta all squared. I'm breaking it down for ease in understanding. So this one is minus 1 now. So at the end of the day, I have 1 minus 1 over 1 minus cos theta all squared. So we have gotten our 2y dx squared. Please, I want you to notice one place. Because of the way this is, when I wanted to differentiate the y dx, again, that is to get the 2y dx squared, I did something. I said the 2y dx squared will be equal to d theta into sine theta over 1 minus cos theta into the theta dx. Please, this is a very important key for the second differentiation, second differential. And I got this one from the initial differentiation here. Please take notes. I got this one again coming back here. So after differentiating this separately, I multiplied by this one, as in the reciprocal of this one. Please take notes. You are doing one more. Now I have another one. X equals 2 cos cube theta. Y equals 2 sin cube theta. X equals 2u cube, where u is equal to cos theta. So the x, the theta, will be equal to the x du times du the theta. I believe you got it now. Chain rule. And what is du the theta? Is equal to minus sin theta. Minus sin theta. So the x, the theta, will be equal to 2 times 3 times u times minus sin theta. So it's going to give me 6 minus 6 sin theta u squared, which is minus 6 sin theta cos square theta. That is dx d theta. Dy d theta. If I follow the same pattern, I'm going to have 2 times 3 times cos theta times sin square theta, which is 6 cos theta sin square theta. So you can see I've gotten dx d theta, dy d theta. Therefore, dy dx is equal to dy d theta times d theta dx. And dy d theta is 6 times, 6 cos theta sin square theta. The theta dx is 1 over minus 6 sin theta cos square theta. So this one gives 1 here. This one cancels 1 here. This I have minus 1 here. And I have sin theta over minus cos theta, which is minus tan theta. So that is dy dx minus sin theta. Dy dx is minus tan theta. So dy dx is minus tan theta. Now let's quickly do the 2y dx squared. So the 2y dx squared is equal to d dx minus tan theta, which will be equal to d d theta minus tan theta d theta dx. You remember? Now, what is d d theta minus tan theta? That is minus sec square theta. What is d d theta? What is d theta dx? That is 1 over minus 6 sin theta cos square theta, which is equal to minus 1 over cos square theta times 1 over minus 6 sin theta cos square theta, which is equal to, this one cancels, 1 over 6 sin theta cos raised to power 4 theta. So with this, I have illustrated how to do the second differentiation. So we will be applying it in some other things later in the future. So with this, I believe you have understood how to handle it. Now, let's look at another place where we apply differentiation. Motion. If you really look at how we started the topic of differentiation, it is about instantaneous change, rate of change. That is, one quantity increases or changes, and there's another corresponding change in another quantity. So at the same time, they have certain relationship. That is what brought about the study of differentiation by Leibniz and Newton. Now, mainly right from kindergarten, we have been learning about speed, distance, and later on in our physics, we also know about velocity, acceleration, which means that velocity also changes, and we have acceleration. Even now, we are told that acceleration can also change, and then we have something we call jerk. What is all this talking about? It's talking about rate of change of motion with time. Now, in this place, we talk about displacement mainly. When you see distance, we might, we replace it with displacement. Why? Because we consider the direction. Mainly, we consider the direction. So when you talk about bearing and whatever, so many times we talk about direction, but most times, at least for this kind of study, we don't talk about straight line motion. And if the distance is in certain direction, we always try to denote that when it's going in certain direction, it is positive. When it's going in another direction or in the opposite direction, it is negative. Just like we have the Cartesian axis, So we might take the right side as positive. So if the motion is towards this place, it is negative. You understand? Just like when we are adding negative numbers and whatever. So, we say addition is towards this place, subtraction is towards the back. So that is how you should view this situation as well. In the same way, we also have speed, and which we can also talk about velocity. Here, we now have acceleration. Well, they said we have jerk now, Sha. They said we have jerk now. So what am I trying to say? If you look at this, these are the quantities we use mainly when we talk about vectors. All these ones are vector quantities. So we talk about vectors. But in this instance, you don't need to trouble yourself if it's a vector or whatever. It is mainly vector when we look at it in this class. So you consider one direction positive, you consider the other direction negative. You don't bring in the angles and whatever in this class. You don't bring in the angle of direction. So, but in this instance, that is all. That is, it moves in one direction positive, the opposite direction negative. So if the velocity is increasing in this direction and moving towards this direction, it's considered positive. If the velocity is towards this direction, it is negative. And if the acceleration is positive, it will be increasing the velocity. If the acceleration is negative, it will be reducing the velocity in the positive direction. But if the velocity is in the opposite direction, and it is increasing, it means the acceleration is negative in the opposite direction. Do you understand? That is, if v is towards this place and it is increasing, it means acceleration is negative towards this place. It will be increasing the velocity in the negative direction. But if the body is moving like this and the acceleration is against it, this one will be reducing. That's what I'm trying to say. That's simple physics. So don't let me go on and start teaching physics now. Now let's look at rate of change, the main thing we are studying now in motion. Now this is the first place of application of differentiation, mainly in real life. In real life. And let's denote our distance with x. So here, we are trying to see if we can use a function to represent the distance from a specific position, which means that we'll be able to express x in terms of t. You can see, if we can do this, and because we can plot graph easily with the knowledge of differentiation and some other things we know, we can draw the graph of the motion. We can easily predict this will be the distance at a certain time. X can be in terms of v, it can be in terms of acceleration even. Yes, but in the basic form, let us leave it as in terms of t, in terms of time. Now, which means that if you look at v, velocity, we say it is the rate of change of distance with time, of displacement with time, of distance with time. Let's use distance. So which means that velocity will be dx dt. Very simple. You can see where the simple application of differentiation comes in. And then you can just say this one is ft, f complement. We also know that velocity too changes. And what does that mean? We call it acceleration. It is d v dt. And that is d dt x. Sorry, d dt dx dt. You can see. And that means it is the 2x dt squared. So you can see. Just like application of the second differential. Just like the application of the second differential. So if I can use an equation to express this in terms of t, it means I can say this one is dx dt. And this one too will be the 2x dt squared. So, another thing I want you to know is this. We know that acceleration is positive. Retardation is negative. That is, it is slowing down the velocity or pushing the velocity to move in the opposite direction faster. Now you can see what you are doing now. It says, discuss the motion of a particle traveling along a straight line such that t seconds after the start, its distance x meters from a fixed point on the line is given by x equals t squared minus t. Illustrate graphically. How do we go about this? We have this x equals t squared minus t. That is the distance from the reference point, the distance from the datum. So, from this, since the distance is given in terms of t, we can find the velocity in terms of t as well. So, v equals dx dt, which is 2t minus 1. And with this, we can find the acceleration. A equals dv dt, which is equal to 2. So, we have gotten our important quantities. From here, we can know the distance from that reference point when t is 0, and some other distances we need to find. So let's look at it. When t equals 0, that is where it started from, x will be equal to t, okay, t minus 1. So 0 into t minus 1. 0 minus 1. So that is 0. So which means that it started from that original point. At the same time, let's look at something. What is velocity when the time is 0? 2 into 0 minus 1. So which means it is reversing. Which means that the motion started by the particle reversing. Let's A at all times is equal to 2. So acceleration is constant. So A is this. Now, let us try to find something as well. When is x 0? There are 2 points at which x is 0. This one is used to denote the time. X equals 0 when t equals 0 and 1. From here, when you factorize this, x equals 0 when t equals to 0 and 1, which means that it initially, let's call this place the reference point. It started from here, it initially moved back, and then came front. Do you understand? So which means that this occurs when time is equal to 0, and this one here when time equals 1. You can see. Let's look at another thing. At what time is velocity 0? At what time is velocity 0? So velocity equals 0 when we have 0 equals 2t minus 1. So 2t equals 1. Therefore t equals half second. So you can see, which means that at this point, when it got here, this is 0.5 seconds. It stopped and then started moving forward. I hope you understand it now. When it started from here, it reversed. When it got to time 0.5, it did what? It stopped. And then it moved back. It started moving forward. That is how the motion occurred. Now, we can also do something. By what distance did it travel backward? By what distance? So that can be gotten by inserting t half. T half inside the first equation. So x is equal to half. So you can see, it is negative. Why? Because it reversed. So this case, time is 0.5 seconds. V is equal to 0. And distance, x is equal to 1/4 meters. Now, by what speed did it start the motion? We can got that by inserting 0 into this place. By inserting 0 into this place. So if you look at it, V0 is -1. Yes, we've gotten that one. So it started with -1 meters per second. So you can see, with this, you can easily describe how the motion took place. And then you can form table. By forming table now, you can now illustrate it graphically, and then look at the graph and say, oh, at so time, this will be the distance. At so time, this will be the velocity. At so time, this will be the acceleration. Let's do that now by making table. So now let's look at this. Look at the distance, the first place. So it reversed back by 1/4 meters. After half second, it stopped. You can see it stopped. That's why we have 0 meters per second here. And then it moved forward. And from there, it started moving on straight. That is what this illustrates. You can see the motion continued. The motion continued straight. But what happened in the first place? It initially reversed. We had negative velocity. So the velocity was negative. And it got to 0. And then from 0, it changed direction. But why did it come to a stop? The acceleration was to increase it. You see? This is negative. So the acceleration is to increase the velocity. So the acceleration is pushing it towards the positive direction, while it is going towards the negative direction. But the acceleration is you know, constant. At a point, it had to stop, and that is why we had it stop at half second. And from there, the acceleration continued acting on it, and it pushed forward. And from there, henceforth, the acceleration continued acting in the positive direction. So, the only negative motion we had was from 0 second to half second. But from half second till afterwards, it's positive. Velocity, positive. Distance, from here to here, the distance was still negative. Do you understand? From the half second to the 4 second, the distance remained negative. Do you understand? So from that place, it continued to be positive. That's all. So with this, we can easily draw graph. And with the graph now, you can easily say, oh, at so time, maybe at 2.5 meters, at 2.5 seconds, this is the distance of the vehicle from this place. You can use the equation, or you can use the table or graph. So whichever way. So now, this is just to pinpoint how to use the knowledge of differentiation in solving motion problems. Let's draw the graph. Let's draw the graph. Now, when t is 0, this is for t, which is second. This is for x, which is meters. When t is 0, the distance is 0. So it initially moved down to half second. So it moved to 1/4. That's, you can see it is negative. And from there, it started moving upward. So you can see. This is a very important point in the drawing of curves. Very important. We refer to it as stationary points, the minimum points. That's what we are going to study at the next level. So I just want you to know these important points. You can see that this is corresponding to where velocity is 0. That is, the x dt is 0. It corresponds to the x dt is 0. So it is very crucial in the graph. Now, before we go on, I want you to see the graph of the velocity and acceleration. You can see that the acceleration is constant, straight. You can see that of the velocity. It is. Now we have another one. We have to discuss about the motion of particle moving with x equals t cubed minus 12t squared plus 36t plus 2. So we have x equals t cubed minus 12t squared plus 36t plus 2. So, which means that its distance from a point is described by this. Its distance from a point is described by this. The previous example we did, the point where we refer to as reference point is where that particle started motion. But in this instance, we will also check. That is by slotting 0, substitute t with 0. Or substitute 0 for t. Now, let's get v. And that is the x t. That's 3t squared minus 24t plus 36. What is our a? The 2x dt squared or the v dt, which is 60 minus 24. From this, we can extract some important information. When t equals 0, what is our x going to be? X is equal to 2 meters from the reference point, which means that it's not starting from the reference point itself. There is a distance between that particle and the reference point. What is our v? Our v is 36 meters per second squared. What is our a? Our a is minus 24 meters per second squared. So, which means that it started 2 meters from the reference point, 1, with velocity 36 meters per second, but it was decelerating, which means that it was slowing down. It was slowing down. The motion, the velocity is positive, acceleration is negative, so it was slowing down. That's what that one means. Now, I might not be able to find the point where x is 0 easily. But I can find the point where v is 0. That is, at the point it stopped. You know, I told you, this one is reducing the velocity. So after some time, the velocity will come to stop. After some time, the particle will come to halt, will stop. So let's find the point where the particle halted. So v equals 3t squared minus 24t plus 36. So which I can easily write as 3 into t squared minus 8 plus 12. Let's quickly factorize it. Minus 2t plus 12. So what does that mean? It shows that velocity will be 0. V is 0 at time t equals 6 or 2. So you can see, it means that there are 2 points where this particle stopped, where its velocity became 0. At time t equals to 6 and time t equals to 2. We will have to investigate further. I think those are the important points. We can check. So t, let's draw the table so that we'll be able to describe how the motion really took place. Now let's use this table to explain the motion. Now, we were told that it started 2 meters from the point of from the reference point, sorry. So that's what it shows here. That it started 2 meters from the reference point. And let's look at what that will be. So if this is the reference point, it means that from here, it is 2 meters from the reference point. And then it continued in that form. Moved 25 meters further. And then it goes to 27. And then 34. 37 meters further. So after getting to 34 here, what happened again? It reverses, it reduces. And it got to 29. That is 5 meters backward. So from here. And then it got to 18, that is 11 meters further. From 18, it got to 7. That is 11. From there, it got back to 2. After getting back to 2, there's change. It paused here. When it got to 34, please don't forget, it paused. So we are looking at the 2 here. It paused here. It paused here again. So from here again, it started going forward. It moved 15 meters away from the starting point. That is 13 meters. This is 13. But from here to here is 15. Please take notes. And from there, 36. That is, it moved 21 meters further. And from there, 63. And like that. So, with this, we can really see how the motion really took place. And what happened? You can see that the velocity was positive here. So the distance increased. Velocity is positive here. The distance increased. It paused. The velocity is negative here. The distance reduced. 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 0. The velocity is positive. It increased. 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 You can see the effect of the velocity. Now let's look at what happened between acceleration velocity and the distance. The acceleration is negative in the first initially. So it reduced the velocity. You can see. It reduced the velocity. The rate of increase of the distance is very low, from 27 to 34, because the velocity has reduced. You can see. So like that, it continued like that. At the point it paused. Because it has paused, the acceleration remains negative. So it affected the velocity to still be negative, to become negative. So there is reversal. So that is how you will see the form, where you can view it, the motion, using differentiation or calculus in general. So I can challenge you, after studying velocity, after studying differentiation or calculus in general, go back and study motion in mechanics or physics. Study it again, no matter what level you are. Study it again, and you will see how fun it can be. So look at the acceleration time graph. In this instance, the acceleration is not constant. You can see how it leads. It moves straight. It started from -24, and then it's increasing. It's in points. To the 4th second, the acceleration is negative. So from here to here, it will be reducing the velocity. It will be affecting the velocity, either from positive towards 0, or from 0 towards negative, or negative towards negative. That is what the effect it will be on velocity from this place to this place. But from here to here, the effect on the velocity will be increasing the velocity in the positive direction. So it will increase it maybe from negative to 0, or from positive or 0 to positive. That is the effect of the acceleration from the 4th second till afterwards. So you can see from here, you can see it is positive. And if you look at it, the velocity is increasing from that place. You can see in the positive direction. Now let's look at the velocity time graph. Now let's look at the velocity time graph. It started from 36 meters per second, and it was reducing until it got to 2. At that point, it became 0. It became 0 there, you can see. And that is the turning point for this distance. It continued until it got to 4. When it got to 4, it turned. That is where acceleration is 0. Look at it. That's where the acceleration is 0. So from there, it started moving upward again. You know, from 2 till it got to 4 seconds, the velocity is negative. So at this point, since the velocity is negative, it will be reducing the distance. That is, it is moving backward. And yet, here again, it still continued. The velocity still remained negative. You can see, it is still moving backward, reducing the distance again. Now, from this point, when it got to 6, this is 6, the velocity became 0 due to the effect of acceleration. And then from there, it became positive. And then the distance, since the velocity has become positive, the distance will be increasing. It will be increasing. So that is the effect. And if you want to find the distance, if you can find the area between this and this point, the area between this point and this point, the area between this point and this point, you can find the total area, the total distance, or distance from certain time to another time. That's one you can easily do applying integration. Now, this is where we illustrate the distance from the reference point graphically. It started 2 meters from the point, that is it, and it continued moving. It got to 27 meters, 34 meters. You can see. 1 second, 27, second, 34. This is positive. And when it got to 34, the velocity became 0, which makes it to be the turning point. And what does this mean? It means the gradient here is parallel to the t-axis. So, which is 0. It now turned back. From there, it turned back. Negative. It's negative down. And then, so, when it becomes negative, it means the value is reducing. You can see. When it got to 2, it became 0 again. So, which means that it was ready to turn again. The gradient here is 0. So, from here, it's turned upward again. So, that is what this graph is